I want to start this video with a quick review of what we mean by similar figures. And before watching this video, you should have had a chance to explore and discuss this concept in class. But here's a quick summary. Similar means that two figures have the same shape, but often different sizes. So a reduction or an enlargement one of the other. And mathematically, that comes down to these two things. That the two figures have corresponding angles which are equal, and corresponding sides which are in proportion. Here's a quick visualization just to remind you of what that means. I have here two figures. One is a larger version of the other. And what makes them similar is that no matter how I change them, the corresponding angles line up. So there's the angle R's being the same. There's the angle P's being the same. The angle Q's being the same. And the angle S's being the same. So all of the corresponding angles remain the same no matter the enlargement or the reduction that I'm dealing with. And the second thing is that if I take matching sides, corresponding sides, so for example PQ and P prime Q prime, and I have them measured here and here, or PR and P prime R prime, and I divide corresponding sides, so this side divided by this side divided by this, you'll notice that the ratio I get is the same. And this is what we mean by the sides are in proportion. They have the same ratio. So when I expand my figures to something like that, the ratio of 2 means that my one figure is twice the size of the other. 1.68 times the size of the other. 70% of the other. Now, when you want to check whether two figures are similar, that means that you will need to check that both of these things are true, that their corresponding angles are equal and their corresponding sides are in proportion. Okay, having said all that, I now want to talk specifically about similar triangles, three-sided figures. And the great news about triangles is that triangles can be shown to be similar by knowing that only one of these two conditions is true. Because if one is true, it can be shown that the other one will automatically be true. So for triangles, we don't need to show both conditions. We just need to know that one or the other is true. So for example, what I'm saying is, let's suppose I had a triangle here, and this first one's twice the size of the other, let's say. Let's suppose this is 6 and 3, 10 and 5, 8 and 4. I can check whether these triangles are similar by taking corresponding sides, 10 divided by 5, 8 divided by 4, and 6 divided by 3. And if all of the ratios come out to the same, which I can see that they do, a ratio of 2, meaning that the one figure is twice the size of the other, knowing that the sides are in proportion, with triangles only, I would therefore know that corresponding angles were equal. And the reverse is true as well. If I knew that the three angles in one triangle equaled the three angles in the other, then I would know that the sides are in proportion. So here's how we're going to put this important information to work. We're being asked here to find the missing sides in the triangles below. And the first thing I'm going to look at is whether I have similar triangles or not. It certainly seems as though we have one triangle, which is a smaller version of the other. And in fact, if I took this triangle, and if I rotated it, and then expanded it, it would perfectly match the other one. That's what we mean by similarity. A smaller version of the other figure. Alright, let's look at this a little bit more precisely mathematically. I don't know if the sides are in proportion or not, but if I know the angles in one equal the angles in the other, then I will know that the sides are in proportion. So what do I know with these two triangles? I know that that angle and that angle are the same because they're vertically opposite. I'll notice that these little arrows mean that I have parallel lines. And parallel lines means that the alternate interior angles are equal, so those angles are equal. And in the same way, these two angles are the same. So we have three angles in one triangle equaling three angles in the other triangle. So I'm going to write triangle ACF is similar, that's the similar symbol, and then my notation has to match. Angle A in this triangle has the same angle as P in the other. Angle C matches angle E in this triangle, and angle F matches angle F in the other triangle. So our two triangles are similar by 3 angles in one equaling 3 angles in the other. And my abbreviation for that is AAA. And because I know that 3 angles are equal in the two triangles, I therefore know the sides are in proportion. Because remember, for triangles, if I know one of the similar conditions, the other one will automatically hold. Alright, so that means that I can relate corresponding sides. So what are the corresponding sides? Well, I can look at the figure or I can look at my notation. I'm going to do it both ways. I can see that AC would match up with EP as I showed when I rotated it. I can also get that match by looking here at this symbol. AC should match PE. So I can write AC divided by PE. That ratio of sides should equal the ratio of the other sides. And the other sides would be CF would be another set. That's this side here. CF would match with EF, this side here. Okay, so let's write that up. CF divided by EF. And finally, if I take the first and last letter, AF divided by its corresponding piece, PF, should have the same ratio as the others. So these are the sides which are in proportion. If I divide the sides, they have the same ratio. Alright, let's write in what we know in terms of lengths. AC from the picture is 11 centimeters. PE is 7. CF is 14. EF is unknown, so I'll leave that as EF. And AF is unknown, and PF from the picture is 6. Alright, and so I want to find missing sides EF and AF. Alright, so we have 3 ratios here. I'm going to work with 2 of them at a time. I'm going to work with these 2, the one that has all the numbers there, and one missing item, EF. And I'm going to solve this proportion, which, remember, I can solve a proportion by cross multiplication. I know that this times this, which would be 98, needs to equal 11 times EF. And so if I isolate EF by dividing by 11, I'm going to get 98 over 11, which is an exact value. That would be 8.90, the 90 repeating. So I actually have an exact decimal for that, 8.90 centimeters. Okay? And now I'm going to go and work towards finding AF. And what I'm going to use this time is this first fraction and the second. I'm going to use the one with all the numbers. And that's going to be the same proportion as AF over 6. Cross multiply. 11 times 6, 66, equals 7 times AF. Divide by 7, so AF is 66 over 7, which I can leave like that, or I'm going to decimalize that one as well. And that's 9.43, but that's an approximation. So let me use the squiggle. That's approximately 9.43 centimeters. Alright, here's another question. What we want to do here is we want to find the length of PA, which is this distance here. I'm just going to mark that with an X. And we're given some other lengths. PB is 7, AM is 4, and AL, which is this distance, is 5. And it looks as though we have similar triangles in that I have a smaller version of one figure is a smaller version of another, it seems, Now we have to test that out. We can't just go by what we feel. But if I take that and I were to move it up and expand it, it looks like it would match the other one. That's the gut feeling way to check for similarity. Now let's do the mathematical way. The mathematical way is to check, do I have 3 angles in one triangle equaling 3 angles in another triangle? And what I'm going to do here, just to make it easier to see perhaps for some of you, is I'm going to separate the big triangle and the small one, putting the corresponding letters on. And the question is, does angle L in this triangle equal angle L in that triangle? And you say, well, of course it does, because it's the same angle. So that's true. Does angle P, which is here, equal angle A, which is here? And the answer to that would be yes, because we have parallel lines. We know that the corresponding angles are equal. And similarly over here, that angle will equal that one. So I do have triangle PBL similar to triangle AML, because 3 angles in one triangle equal 3 angles in the other. And because that's true, I then know that the corresponding sides are in ratio, are in proportion. Okay, so let's separate the sides in the individually drawn triangles. This is 7. This is 4. This is 5. Now this distance here would be this whole distance there, which if I add those two things together, I get x plus 5. All right? I have no information about the other two sides, so I'm going to not use that information. I'm going to leave it out. All right, so let's match up corresponding sides. Which sides match? X plus 5 and 5 match up. We know that because PL in our written symbol matches AL. That's this side and this side. So we can therefore say that x plus 5 over 5 will equal 7 over 4. That was P. What we just used there, again, was PL divided by AL equaling PB over AM. All right, so now I have a proportion to solve, and I can do same thing I did before. I can use the cross multiplication method. 5 times 7, 35, must equal 4 times x plus 5. And we've created a little equation for us to solve here, so we can distribute, subtract 20, divide both sides by 4. So the length of x is 15 over 4, and remember that x was PA, which is what we were asked to find. Therefore, PA is equal to 15 over 4 centimeters.